Alrighty, howdy folks. Let's go with chapter 14, section 7, which is about maximum and minimum values. I figured one good way to talk about this is to recap something of the kind that you did in Calculus 1. We did talk about max and min for just a y equals f of x, a single variable function, right? So let's recap that. Let C be a number in the domain D of a function f, then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D. Whoa. Okay. It might look complicated when you take a first glance at it, but in fact, it's fairly straightforward. You have to have a number C, and that C should be in the domain of the function. Okay, if that is the case, we could call the y value at that particular C, f of C, as the absolute maximum. Under what conditions? You can say that is the absolute maximum value of that function f on that particular domain if it so happens that y of c is bigger than every other f of x, bigger than or equal to, okay, for all x in the domain. That kind of makes sense, right? Hey, where is the absolute value, absolute maximum of this function? And you'll say, where is the highest value? What is the highest value? Or where is the highest value of this function? And you will go to some particular x value and say, here is where we are noticing that the function has the highest value. And we'll say, yep, that's the absolute maximum. As simple as that. Similarly, absolute minimum is where the function has the smallest y value, right? Okay, here, pictorially, obviously, here is where the function has the maximum value. And so the corresponding x, that C, let's call it C1. C1 is where you have the absolute maximum. Cool. And C2 is where we have the absolute minimum. As simple as that. Okay. Now, the absolute minimums and absolute maximums are fairly straightforward intuitively. But then there comes a clear an absolute minimum. Yeah. Okay. But then there comes something called a local maximum. That's just a little less straightforward. Let me put it that way. That's just a little less straightforward. What do I mean? The number f of c is a local maximum value of f if f of c is greater than or equal to f of x for all x. It almost looks like the absolute maximum's definition, right? But here is the difference. For all x on an open interval containing c. That's the key. So f of c must be bigger than or equal to all the f of x's where x's or x values are in the neighborhood of that c or in the open interval containing. I'll show you with an example. I'll show you with a picture exactly what I mean. Similarly, local minimum can be defined as f of c less than or equal to f of x for all x on an open interval containing c. Here is what I mean by that. Let's take a look at it. Here, what's the absolute maximum? Let's go back to our absolute maximum. So you look at, there is a pretty high value. Is that the absolute maximum? And you'll say, nope, this value is bigger than that. Okay, cool. So it looks like this is the absolute maximum, right? And which one is the absolute minimum? This is. But then when it comes to local minimum and local maximum, do we have a local maximum at A? The answer is yes. But come on, man, there are other values that are bigger than this. Yeah. But in that small localized neighborhood, this is the biggest one. How do we know? We know because we can, and let me first show you all this. So there is a local minimum at B and another local maximum at C, a local minimum at D is the claim. Now, at A, we have a neighborhood, right? In that neighborhood, that means in this open interval containing A, what is that? An open interval. The very fact that I have parentheses here means I'm talking about an open interval. And that open interval should contain A. If our claim is, hey, there's a local max at A, well, you better have an open interval, and that open interval better contain A. Okay, now you ask the question, is f of A bigger than every other f of x in that neighborhood? So if I pick x here, the corresponding f of x is that y value. Is our y value of f of c or f of a here, is f of a bigger than that f of x value? Yes, it is. Similarly, if I pick another one, any other x value within this open interval, f of a is bigger than every one of those f of x's. Because that happens, we can confidently claim that there is a local max at A. And now you can see, similarly, at B, we have a local minimum because we have local minimum, and this happens to be an absolute minimum also. There's a neighborhood, there's an open interval where this guy is the smallest, right? F of B is smaller than every other f of x in that neighborhood or in that open interval. At C, we have a local maximum and an absolute maximum. At D, this is the whole idea. So the main point is this stupid concept called neighborhood. There's an open interval surrounding this is the idea. Cool? Okay, let's move on. Oh yeah, this guy. This is another thing that we learned in Cal 1, which is the extreme value theorem. Now, one thing you must know. The moment you have a theorem, it's an important one, and it's especially important if it has a name attached to it. The name could be that of a person, for example, Fermat's theorem, Rolle's theorem, Lagrange's theorem, or something like the mean value theorem, the extreme value theorem, fundamental theorem of calculus. If you have names like that, those theorems are ridiculously important. In our level, maybe not, but the moment you go to some higher level classes, pure math classes, you will be using those theorems so frequently that your head will spin. Okay, all right, so let's see. What is this extreme value theorem? It says if f is continuous on a closed interval AB, that must happen. F must be continuous on a closed interval AB. That means it must be defined even at A and at B. That is the key. The closed interval means at A, it must be defined. Otherwise, we will have to make the A a parenthesis to the left of A, right? Because A is not included. Now, in this case, that doesn't cut it. The function must be continuous even at the endpoints A and B. Okay. And then f attains a minimum value f of c and a minimum value f of d at some number c and d in the closed interval AB. That's what this theorem is guaranteeing. Let me repeat that. What this theorem is saying is, if you have a function defined on a closed interval AB and is continuous on the closed interval AB, this theorem is guaranteeing something. It says the function is guaranteed to have an absolute maximum and an absolute minimum somewhere in that closed interval AB. Cool. Well, is that true here in this figure? Yep, this function is is continuous on this closed interval. And sure enough, there is a maximum, absolute maximum at C and an absolute minimum at D. Okay, let's see. Well, there is no absolute maximum here, man. No, there is at B. And see, now you could have absolute maximums and absolute minimums and slash or absolute minimums at the end points, at the extreme points. That's perfectly possible. So you're guaranteed of this. That is the greatness of this extreme value theorem. So all you need to do is show that the function is continuous on a closed interval, and then the theorem guarantees that you will have an absolute maximum and an absolute minimum. Cool. All right. Some simple questions. Do we have in the figure below, state whether the function has a local max or local min or absolute min at the stated points. Okay, at A, do we have a local max or local min? Well, that's a hollow circle. That's not even defined. Since f is undefined at A, yeah, so forget it. At, whoa, huh, what happened? I thought I would have more things. Okay, at D, what do you think? Do we have a local minimum or a local maximum or anything like that at D? The answer is yes, there is a local minimum at D. That doesn't seem so obvious. Well, the thing is, if we come down, can we come up with an open interval surrounding the x value of D, where this is the y value at D, f of D is this guy, and is that the smallest in that interval containing this x value of D? Yep, it is, right? And so there is a local minimum here, and similarly there's a local max there, local min here, local max, and here, well, that's a little difficult. Yeah, okay, let's look at that. Can we claim that there is a local min at n? Yeah, let me answer that question. That's a challenging one. Is there a local min at n? The answer is no. Why not? Because we must have, if we go to the definition, we must have an open interval containing this. So if I make an interval to the right, well, that function is not even defined there. So I cannot check whether or not this is the smallest in that interval, in the interval containing n at all. So the answer is no, you cannot say there is a local min at n. Okay, all right, enough of that. Let's now go to what we are supposed to learn in Calc 3.
No snow.
You will notice that you will notice.
When you
Alexa,
see the
stop.
light ring on your...
Sorry about that, guys. If we look at the definition for multivariable functions, like z is a function of x, y, you will notice that all this is very similar to the one that we learned in Cal 1. That's why I wanted to recap all that. Cool. A function f of two variables has a local max at AB, the ordered pair AB, if f of xy is less than or equal to f of AB for all xy in the neighborhood of AB. Okay. Over there in Cal 1, when we talk about neighborhood, we simply mean an open interval containing that point whatever, C or A or whatever, right? An open interval containing. But then in Cal 3, when we say a neighborhood of AB, that's what we say. And that number f of AB is called a local maximum value because in that neighborhood, that has the biggest Z value. And neighborhood actually represents, what that means is, it refers to all the points in a disk with AB as center and some radius r. So instead of an open interval, we'll have an open circle. That's the difference. And that circle has some radius r. Okay? Now, and we can describe a local minimum in a similar way, right? In the sense f of xy is greater than or equal to f of ab, or f of ab is less than or equal to f of xy, then we have a local minimum at ab. Cool. Theorem. Ooh, this is an interesting one. If f has a local maximum or minimum at AB and the first order partial derivatives of f exist there, then f sub x of AB is equal to 0, f sub y of AB equals 0. What does that mean? If f has a local max or min at AB, apparently the first derivative partial f with respect to x is guaranteed to be 0 and partial f with respect to y at AB is guaranteed to be 0. Isn't that interesting? If you have a local maximum or a local minimum at a point, the partial derivatives, both with respect to x and with respect to y, each of them rather, is going to be 0. Now comes an interesting question. What is that? If f has a local max or min, the derivatives are 0. Oh, is it saying if the derivatives are 0, you are guaranteed to have a local maximum or minimum? You see my question? Please pay attention to that question. Based on this theorem, can we conclude that if the partial derivatives with respect to x and with respect to y happen to be 0 at a certain point, can we say, yep, dude, you're guaranteed to have a local maximum or local minimum at AB? Can we say that? Is that what the theorem is saying? The answer is an emphatic no. Why? But that's what it's saying, man. No. So this is where you need to understand the difference between a theorem and the converse of a theorem. Or a theorem is like a conditional, if P then Q. And the converse of it is if Q then P. If F has blah blah blah, then blah blah, right? If P then Q. If P then Q is true does not mean if Q then P is true. That need not be true. Okay. For example, if X is a poodle, then X is a dog. Is that true? If X is a poodle, then X is a dog. Yeah, man, like you pick an animal and that happens to be a poodle and guaranteed that poodle is a dog. Now, does that automatically mean that if X is a dog, then X is a poodle? No, because I could very well pick a dog, but it is not a poodle. Instead, it's a Doberman or a Labrador. Let's go with the cute ones. I'm not saying Dobermans are not cute, they are, but Labrador puppies, man, jeez. They steal my heart. If I see a Labrador puppy, I'm just, Anyway, so there, if Q then P was false, so that's what you have to be careful about. If the partial derivatives are 0, does not mean there is a local max or local min. There could be, that may be true, but you cannot guarantee that is the question, is the point. All right, definition. Okay. A point AB is called a critical point. Yeah, we need to define critical points. Or stationary point if partial f with respect to x or partial f with respect to y is 0, or something else could happen. If one of these partial derivatives does not exist. What do you mean partial derivative does not exist? Yeah, for instance, let's say there is a division by 0 issue. Then at that point the function is, the derivative, partial derivative does not exist because you'll be dividing by a 0. Right? That's the idea. Okay, so you would call them a critical point. And the second derivative test, yeah, this is an interesting one. Suppose the second partial derivatives of f are continuous in the neighborhood of AB. So you take the second derivatives and they exist, and not only that, they are continuous in the neighborhood of AB, let's say. That's the first condition. And also suppose that the first derivatives are 0, first partial derivatives are 0. Then if we were to define something called M, you figure this out. You better pay attention to this one. We are going to solve quite a few problems based on this one. Okay, you need to compute M like this. Either you can use this formula, or for me, I feel this determinant to be much more convenient form of expressing this. Basically, you're saying fxx, second partial f with respect to x, second partial of f with respect to x and y, second partial of f with respect to x and y, and like this. If you figure this determinant out at a and b, at ab rather, then if there are few different cases. If m happens to be greater than 0, and in addition f sub xx of ab is greater than 0, then we can say then f of AB is a local minimum. If one of these second derivatives is greater than 0, and in addition, you must have m to be greater than 0, this determinant, then you can confidently say, then f of AB is a local minimum. Well, if you recall, the calculus 1 version of this is when we say, let's say dy dx is equal to 0, or f prime of some a is equal to 0. Is there a minimum or maximum value there? You say, wait a minute. Let me evaluate the second derivative, we say. Okay? And if the second derivative is negative, let me repeat that. If the second derivative is negative, then we'll have a maximum at that point, a local maximum at that point. Why is that? Well, a second derivative is negative indicates that that function is concave down. Think of an upside down parabola. I wish I had a figure ready as I talk about this. I apologize. Now imagine an upside down parabola. Okay, y equals negative x squared. Would you agree that an upside down parabola is concave down? Now, that means the second derivative is actually negative. Let's pick, f of x equals x squared. F prime is 2x, and f double prime is f of x is equal to negative x squared if it's an upside down parabola. F of x equals negative x squared, f prime of x is negative 2x, and f double prime is negative 2. Aha! So the second derivative is negative. That means that parabola is concave down. And because of that, we have a local maximum at x equal to 0. The derivative is 0, f prime of x is 0 at x equal to 0, and the second derivative is negative. We are talking about something very similar to it, but just a tad more complicated. You need to look at m being greater than 0 and f sub x's, xx, the second derivative, second partial with respect to x being greater than 0. Then we have a local minimum. Again, if m is greater than 0, but the second derivative is less than 0, we have a local maximum. This is almost like the concavity being down. Okay. If m is, however, less than 0, then f of ab is not a local max or a local min. Isn't that interesting? If m is less than 0, and the point ab in case C is called a saddle point. Now, what's the significance of this? I'll show you in just a second. So this is a saddle point. Now check this out. If you go back to the previous slide, I said something like this. Yeah, let me go back and show you that. Here, as I was talking about this, if f has a local max or min, then partial derivatives are 0. Then I asked the converse question. Hey, if the partial derivatives are 0, can we say there is a local max or local min? And I said, nope, you cannot say that. Okay, here is this. The saddle point is a classic example of that. If you observe at this point, partial f with respect to x, that means, let's say this is the x-axis. Which way did they take this as? It doesn't matter. Okay, let's say, as before, let's stay consistent. So sticking out of this is the x-axis. Now, would you agree that the partial derivative is 0 there? That means if you were to take a section, a vertical section here, and parallel to the, which plane? XZ plane, you would notice that this is an upside down parabola. And sure enough, the derivative there is 0, which would represent the partial with respect to x. So that derivative is 0. And now, on the other hand, if you were to look at the curve this way, which is oriented in the YZ plane, there partial z with respect to y, partial f with respect to y is 0. So both partial f with respect to x and partial f with respect to y are in fact equal to 0. However, there is no local max here, nor is there a local min here. What? Why not? There is a local max, man. Look at this. It's the high. No, in this orientation, that may be the local max, but then that happens to be the same point, happens to be the local min so far as this orientation is concerned. So should you call it a local max or a local min? Because of that ambiguity, you say neither. You say, nope, there is no local max or local min, and that's a saddle point. We say, why do we call it a saddle point? I don't need to explain why to someone from Tennessee, right? Y'all ride horses, I take it? Because that looks like a horse saddle. All right. What else? Yeah, extreme value theorem from functions of two variables. Earlier we saw extreme value theorem for y equals f of x for function of one variable. And now let's look at for two variables. If f is continuous on a closed bounded set D in R2. Okay, this is sort of the domain. If f is closed on bounded set D in R2, that closed interval AB back in y equals f of x situation that we looked at, then f attains an absolute maximum value f of x1, y1, and an absolute minimum f of x2, y2 at some points x1, y1, x2, y2 in the domain, in that D, in that set D, bounded set. Guaranteed. Cool. Let's look at that again. If f is continuous on a closed bounded set D, then f is guaranteed to attain absolute maximum and absolute minimum somewhere in that set D. Guaranteed is the idea. So what's the procedure? To find the absolute maximum and minimum values of a continuous function f on a closed bounded set D, we follow a few steps. Step 1, find the values of f at the critical points of f in D. So find the critical points. How do you find the critical points? Well, partial f with respect to x and partial f with respect to y, set them equal to 0. So are those things 0 at a certain point, partial f? Or it's possible that partial f with respect to x or partial f with respect to y is not defined there. Okay, you got a division by 0 or some situation like that. So that's how you find the critical points. Find the values of f at those critical points. And second, find the extreme values of f on the boundary of D. So on the boundary of this thing, this is sort of analogous to finding the function's values at a and b in the one where y equals f of x situation on the ends of the interval. Here we don't have ends of an interval. Instead, we have a boundary. Okay. So find the extreme values of f on the boundary of D. And the largest of the values from steps 1 and 2 is the absolute maximum value. The smallest is the absolute minimum value. Cool. I will solve quite a few problems to solidify this concept. Cool. Suppose 1, 1 is a critical point of a function f with continuous second derivatives given by these things. What can we say about f? Okay. 1, 1 is a critical point of the function apparently, and the second derivatives are given. What is this talking about? It's talking about using that M concept. Okay, so the first thing we'll do is figure out what the determinant is. M11 is f of xx. So M clearly is equal to -1. And what does that say? If f sub xx is greater than 0 and M happens to be less than 0, then there is a saddle point. The moment M is less than 0, saddle point, right? So there is a saddle point for the saddle point at 1, 1 in this particular case. Okay, next, find the local maximum and minimum values and saddle points of the function. Okay, what are the steps? We know we are given f, so let's first find partial f with respect to x, and first term with derivative with respect to x, clearly y, -2, 0, 2x, 0, right? -2x, so that's exactly what I have. All right, and partial with respect to y is similarly x -2 -2y. And if we set f sub x equal to 0, right, to find the critical points, that's one of the possibilities. Oh, by the way, is partial f with respect to x or partial f with respect to y not defined anywhere? Nope, we can find its value everywhere, right? Okay. All right, I'm sorry, I had to take a sip of water. My throat was getting too dry. All right, if we set f sub x equal to 0, we get y equals 2 plus 2x. Oh, what does that mean? Yeah, maybe I want you to think about this, guys. When I say guys, I mean girls too. I'm not being a sexist here. It's folks. Maybe I should say folks. So if we set f, so we get y equals 2 plus 2x. What in the world does this mean? That means for this function on the line, would you agree that y equals 2 plus 2x represents a line? All along that line, the first derivative, partial f with respect to x happens to be 0. All along that line. That's what it means. Okay. And similarly, if we set partial f with respect to y equal to 0, we get x minus 2 minus minus 2y equal to 0. But then, notice what I did here. Partial f with respect to x is 0 along this entire line. So there are infinite number of points where partial f with respect to x is 0. Similarly, if we set partial f with respect to y to be 0, then we get similarly another line, x equals 2 plus 2y line, right? Or you can solve for y and say 1/2 x minus 2 along that line. But then what's the point of intersection of those two lines? That is where both partial f with respect to x and partial f with respect to y are 0. Would you agree with me? Let me repeat that. This condition gives us where partial f with respect to x is 0. Setting this part equal to 0, we get where partial f with respect to y is equal to 0. Now, where are both 0? Well, set both of them equal to 0 and solve for xy. That's exactly what we are doing here. We are saying x minus 2 minus 2 times, and we are plugging this value of y here. And so that gives us the x coordinate of the intersection point of the two lines. Now, from that we can figure out what the y coordinate ought to be. So, -2, -2 is a critical point. Pay attention to the strategy that we adopted. We figured out partial f with respect to x and partial f with respect to y, set both of them equal to 0 and solved them simultaneously to figure out the critical point or points. Okay, then let's figure out f sub xx and f sub xy and all the second derivatives. And not only that, let's evaluate all of them at the critical point. Since they ended up being constant, the second derivatives are these constant values at any x and y. So clearly, even at our -2, -2, they should have these values. Cool. The idea of figuring out all the second derivatives is so that we can find that m as the determinant. Okay. And so since f(x(x) is less than 0 and m is greater than 0, now going back to that, so keep that particular sheet handy. The different three conditions, m is greater than 0, f sub x is greater than 0, f of x is less than 0, m is less than 0, all those three conditions. Okay. We have a local max, m is greater than 0, but f sub xx is less than 0. Right? By the second derivative test. That's it. Would you be able to do problems like that? The rest of them are kind of like that. Find the local maximum and minimum values and saddle points of the function. Okay, f sub xy, as before, we'll find the partial derivative with respect to x partial derivative with respect to y, and second partials is just a bit tedious, that work, all the derivatives, but the concept as such is the same as the previous one. Okay, now comes the interesting part. Setting the first partial with respect to x equal to 0. So we got all of this stuff. Please pay attention to this part now. So this part we should be set equal to 0. Okay, based on that, I seem to be saying, oh, that means y times 1 minus x square must be 0. But what about e to the negative, man? Oh, well, that never is going to be 0. Exponential function is never 0, right? So if it is the case that the product of these three things is equal to 0, then it must be the case that since that cannot be 0, y times 1 minus x squared, that quantity must be the one that is equal to 0. And that's exactly what I'm saying here. Okay, and now what does that mean? Either y equal to 0 or x is equal to plus or minus 1. Y times 1 minus x squared. Y is 0 or x equals plus or minus 1, right? Similarly, if we set f sub y equal to 0, we get x times, we're going here, x times 1 minus y squared is 0. So we have y equals 0, x equals 0, x equals 1, y equals plus or minus 1, all these situations. Which ones? As a combination, y equals 0. Well, when y equals 0, then x must be equal to 0 according to this. Let me be clear. I'm not being clear. The partial with respect to x gave us two possibilities. One possibility is that y could be 0 or x could be plus or minus 1. Are we cool? And with respect to y gave us two conditions. We gave us this condition from which we could say x equals 0, but let's keep it this way. Now, let's pick up this condition y equals 0, okay, and come to this one. Well, set y equal to 0 here. Then what happens? Then x is clearly going to be 0 because we have x times 1 minus 0 is 1, x times 1 is x, x is equal to 0. And that's what we have here. Y equals 0, x equals 0. And then let's go back and pick up x equals positive 1 and use that condition over here. X equals 1 implies 1 times 1 minus y squared is equal to 0, and then y must be plus or minus 1 because y squared is equal to 1. So x equals 1 gives us y equals plus or minus 1. Now let's come back here and pick up this x equals negative 1. And if we do that, again, we get x equals negative 1, but y is plus or minus 1. Whew. So what do we have now? A whole bunch of combinations of x and y. Would you agree? X, y combinations are 0, 0, 1, 1, 1, negative 1, negative 1, positive 1, negative 1, negative 1. So there are 5 possible scenarios now. This is the idea. So the critical points are all of those things. And so what we now need to do is patiently evaluate all the m values for every one of those things. So we find m at 0, 0, this first guy, and that turned out to be negative. And based on that second derivative test, that must be 0, a saddle point. The moment m turns out to be negative, we have a saddle point. M11 turns out to be 4 over e square. That is greater than 0. Ah, good. But now we look at f sub xx. Oh, this is definitely negative. So f sub x is negative, the second partial with respect to x is negative, and m is greater than 0. So that means we have a maximum, right? Similarly, we got this is greater than 0 and that is negative. M is greater than 0. F sub xx is less than 0. Again, a local max. 1, negative 1 greater than 0. This is positive. So the second derivative, f sub xx is positive. So that means local minimum. And positive, this is greater than 0, that is positive. So again, a local minimum. Cool. And in fact, that function, when I plotted, what was this function? That big complicated one. xy e to the negative x square plus y square over 2. When I plotted that, this is how it actually looks. And let's also look at, there's a saddle point at 0, 0. 1, 1 has a local max. There's a local max at 1, 1 and negative 1, 1, negative 1. Opposite ends, 1, negative 1 and negative 1, 1. We have local, see, maxes there. The diagonally opposite quadrants, and minimums here, diagonally opposite. Okay, and there's actually a saddle point here at 0, 0. Cool. So that's the idea. Okay, find the absolute max and min on the set D. So that set D is given by a rectangle. It goes from negative 3 to positive 3 in the x direction, and the rectangle goes from 0 to 3 in the y direction. So the idea is to use the extreme value theorem. Yeah, this is good. So there's a graph of this one. You remember that extreme value theorem, folks? It says you're guaranteed absolute maximum and absolute minimum. For that, of course, the function must be continuous on this entire D, should I call it domain? Yeah, okay, I could call it domain. Entire domain. This function must be continuous. Well, let's look at that. Is it continuous? Yeah, these are all nice polynomials. So polynomials are continuous everywhere. So definitely, function is continuous everywhere in this domain. And now we will find the critical points. For that, let's figure out f sub x. We have done this before. And also figure out f sub y. Set f sub x equal to 0 and you get this condition. Use this condition and plug into setting f sub y equal to 0. So plug this into f sub y equal to 0. So x plus 2 times negative 2x minus 6. So that gives us x to be negative 2. And also, since y is negative 2x, we get y equals negative 2 times negative 2 is positive 4. Are we good? All right. Now what? Well, is negative 2 4? Is it inside the domain? Negative 2, x is negative 2, somewhere here, and 4. Yep, that's in the domain. So you have to make sure that, in fact, the so-called, before you call this as a critical point, you better make sure that it is inside the domain. Right? Yes, it is true that negative 2, 4 satisfies the conditions. Partial f with respect to x and partial f with respect to y would be 0 there. But maybe that point is not inside the domain. So you first need to make sure that it is in the domain in order to classify it as a critical point. Okay? All right. Next, go ahead and figure out the value at that critical point, and the value turns out to be negative 12. That is simple, right? Okay. What else? Well, now we need to figure out what the values, what the maximum and the minimum values are on these boundaries. That is, along this line L1, along this line L2, L3, and L4. Okay, let's embark on that. Find functions' extreme values on the boundary. We'll now apprehend maximum and minimum on the boundaries. Along line L1, well, there y is equal to 0. So simply, we'll just quite literally, figure out f of x 0 because y happens to be 0. And if we go to the definition of f of xy here, that's given by this. So the second term goes to 0, third, fourth, they all go to 0, and just we end up with an x square. Cool. Well, is there a maximum value of f given that f of xy is equal to x square? And is there a minimum value? X square, we know about this function, right? So at x equals positive 3, this has a value of positive 9. And we know the minimum would be at x equal to 0, whose value is 0. So has a maximum at plus or minus 3, and where the value is 9, and minimum at x equal to 0, so the value of the function there is 0. So what's the conclusion here? At least the initial conclusion here about this L1, along L1. Along L1, we have a maximum value for the function at x equals 3 and x equals negative 3. And that maximum value happens to be 9. And a minimum value of 0 at x equal to 0. X equal to 0, and of course, because already we have y equal to 0, at 0, 0, we have a minimum value. Cool. Now, do a similar analysis at x equals 3. That's L2, right? That's the vertical line where x is equal to 3. How do we do this? Well, go back to this original function f and plug x equal to 3. And so we end up with y square minus 3y plus 9 as the function. And there are restrictions on y. Y is not defined everywhere. I mean, y is restricted to being on the interval 0 to 5. So we are putting that condition. Okay. And in fact, even for the L1, we did put that condition that x is negative 3 less than x less than negative 3 less than or equal to x less than or equal to positive 3. Similarly here, 0 less than or equal to y less than or equal to 5. Cool. All right, so what's the idea? We need to figure out where the maximum and minimum values of this y square minus 3y plus 9 are. So it has a minimum at y equals 3/2. What? Where'd you get that from, man? Any idea where I got that from? Y square minus 3y plus 9 has a minimum at y equals 3/2. Well, you remember, the derivative must be 0. So I took the derivative, which happens to be 2y minus 3, set that equal to 0. So that gave me y equals 3/2. Sure enough, there is a vertex for this parabola at y equals 3/2, right? So that's the idea. X, of course, we already know that x is 3, and so y equals 3/2. We have a minimum because this is a y square minus 3y. Positive y square indicates this is a parabola that is pointing, is a concave up parabola, just like a y equals x square kind of a parabola. Has a minimum at y equals 3/2. And what's the maximum? Well, you got to go to the endpoints. Check the maximum. Where f of xy is equal to Okay, at 3 and 3 halves. Where does this 3 come from? X value is 3 there. On line L2, X value is 3, so that's where this comes from. And that turns out to be 27/4. And a maximum at 5. The y equals 5. So if we were to, at y equal to 0, if we were to look at y equal to, if we plug in y equals 0, we get a 9. And at 5 we have 19, which is bigger than 9. So y equals 5 is certainly bigger. And what else? Similarly, at y equals 5, that is line L3, carry on similar calculations. And I may have summarized the whole thing. Yeah, I did. Cool. And a whole bunch of places we found these values. The first one is the critical point, -2 and 4. This has, the function has a value of -12. And then along L1, we have these values, and L2, L3, and all we now need to do is patiently look at which one is the smallest value. This is -45/4 is less than -12. Oh, so -12 is the smallest. Do you agree? Had this been -48/4, then that would have been -12. But since this is less, -45/4, it's about 11.25. -11.25. -12 is less than -11.25. So the smallest value of this function is -12. And when it comes to the largest, we have a 9. That's bigger than 0. This is 4 times 6. 4 sevens are 28. So it's less than 7. Nope, it loses. This is 19. Yikes, that's pretty big. Here is again another 19. Cool. Ladies and gentlemen, we got the winner. -12 is the smallest and 19 is the biggest. That's it. Right? Can you do some analysis like this, folks? If you can, I'll be a happy man. That's it for this section. Thank you, guys. Thank you, folks.